So the first thing we'll talk about is this thing called molarity. Does anybody know the formula for molarity? Moles over liters. So moles of solute over the liters of the solution. We can't have milliliters when we do this. We got to convert everything to liters. And that is what we know as molarity. So we're kind of counting the number of atoms that are in a solution. So when we deal with molarity, we're talking about counting the number of moles of atoms or ions or molecules in a solution. That's what we're doing. So it's a way of counting. Okay? And I guess this would be concentration, how concentrated it is. Okay? So shorthand for that would be capital M equals MOL over liters. When you do that. So that's molarity. What we're going to do is we'll look at some problems where you'll have to find the molarity, and I'm not going to give you the moles and then give you the liters, because everybody knows you just plug those numbers in and get it. So it's something maybe you have to do a little bit more work in which to get the values you need to find. Okay? So I'm going to go ahead and write the first one up here. All these are in Chapter 4. So we have multiple examples in Chapter 4 you can look at. And they're not the same as what I'm going to write on the board. So this book does an excellent job of giving you lots of examples and details of how to work out the problems. And all you have to do is look in it and find those sections. And you can find, you know, what we do, except for ice. They might have did a little different. And the people on the test did it both ways, and they were okay doing it both ways. I got right answers doing it both ways, whether you use ice or whether you use the method where you have to go all the way through to find your grams and then figure out limiting based upon that. So the first question that we have is, when 30 grams of KBr dissolves to make 500 milliliters of solution, what is the molarity concentration of KBr? So we're looking at the total solution's concentration, not ions, but overall, what's the concentration of that solution? So what's the first thing I need to do?
Find moles.
Okay, find moles. Now you can do this all in one setup, and I'm going to show you all in one setup. Now some of you may decide that you want to do different division to get there. But I'm going to do it all in one setup so that you don't have to do any one calculation. You set up another setup to get another calculation, and so on and so forth. Okay? So everything's in one setup. So, right, I have to change it to moles. So I got that 30 grams of KBr. This would be second nature to you, what you need to do. I don't think there was too many students that missed calculating molar masses on the test. It just takes time to do that, and I thought you did a nice job. There wasn't too many mistakes where you missed maybe, and if you did miss, it was like a half a point, but most of you were figuring it out correctly, and you're getting faster at that because you're getting some things memorized, and just plugging them in your calculator a lot of times. So there's a 119.0 grams of KBr in 1 mole.
Is that 30 or 36 grams of potassium chloride? Okay.
30. So we're at moles. Now we just need to keep going. Some of you will tend to just do the last step and be done with it. But on this first one, I'm going to have my 500 milliliters. So it's per liter. So I got moles. I want to do it per liter. So down below I'll put 500 milliliters. Okay, over 1. So right now it's moles per milliliter. Yes, John?
If you're converting it, shouldn't 500 be on top and liter be on the bottom?
Well, I'm not putting a unit with this. Okay, so this here is just, right now, if I do the calculation, it would give me, what would be my answer? Moles over milliliters. So I need moles over liters.
So why is it to 1?
It's just kind of like a fraction. It's like I don't have to put a unit above. It's kind of like 30.0 grams of KBr over 1. I'm not showing the 1. But what it does is it gets me milliliters on bottom. Okay? So I know it's...
Starting a whole new.
What's that?
It was like if you were starting a new.
Yeah, it'd be kind of like that. It's kind of like I know that. Now, most of you are going to put what down here and be done with it? 0.5 liters, right? And then you'd be done. And then you have moles over liters. And your answer would be completed. I'll do that on the next one. But just to show you, if you wanted to keep going, you could say, well, there's 1,000 milliliters for every 1 liter. Milliliters cancel out. So I have grams canceled out.
Wait, what's that 1 on the top? Sorry.
It's nothing. It's just a 1.
Okay.
Yeah, you don't have, when you do setups, you don't always have to have a unit with a number. Yeah, it's just like, we want milliliters on bottom. It's like having 500 milliliters to the minus 1. I mean, if you want, you can set them up that way too. But. So then my answer would be 0.504 molarity. Any questions with that? So what you want to do is get moles on top, liters on bottom, then you're done. So that'd be 0.504 molarity of the solution you get. Any questions on, we might have to take molarity and we might have to go back and find out how many grams we'd have, so it would be kind of the opposite setup. Very powerful. I probably told you this before, but it's been a long time ago, but once in chemistry, once you figure out how units have to cancel and you can get to the correct units in the final answer by converting, it's so, I mean, you don't have to memorize anything, you just know the process. I've got to get moles on top, liters on bottom for this example. And in examples that you did on the test, the last test, you kind of know how you have to go through to get your final units on that. So, something was very important for me to figure out when I was taking chemistry when I was a sophomore. Very important. So, once I got that figured out, it made things a lot easier on me. Okay, the next thing I'm going to do is show you what happens when something breaks apart in solution. So, you don't have to write this down, but if I have a beaker here that's H2O, and most of these deal with the solvent of H2O. H2O is polar. Polar means one side has a negative charge, the other side has a positive charge. And we're not going to go into reasons how it becomes polar, but oxygen's negative, and the hydrogens are going to be slightly positive. They are called polar molecules. Right? So let's say we have that example of the KBr that goes in. Okay, and we'll just go ahead and show you what a KBr ionic formula would be. It's a bunch of anions that are stuck together alternate ways. And so we'll say that this is Br. Well, yeah, Br negative. And then this here would be K. And when we take and put it in there, what's the Br going to be attracted to?
Hydrogen.
Opposites attract, so the Br will be attracted to hydrogen, and basically this is a process called hydration. When you guys become hydrated, what do you know? What's that?
You got water.
Yeah, you got water. You get hydrated through the day. Drinking water and that, you stay hydrated. It's always good health-wise to drink plenty of water so you become hydrated. So this is a process called of hydrating. And so what this bromine will do will be pulled apart from its original, not molecule, but ionic structure. And bromine would go here, right next to the hydrogen. And then potassium would be attracted to the oxygen. So that potassium would go here. And it will just be pulled apart as it goes in. So what do you do to increase the rate at which that dissolves? We went through that. So what would you do to increase this rate, how quickly it dissolves? What would you do?
Add more
Heat it
H2O.
up.
Stir it,
Stir.
Heat it up.
agitate it, shake it, stir it. What else?
Heat it up.
Heat it up. Most of the times heating it up would cause the water to move faster. When the water moves faster, there's more contact between the ions going in and the water, so it would speed up the process. Okay? Yes?
Crush it. Increase
Crush it up. Yep. If we crush it up, then what happens, the inner crystals in a big block of it aren't in contact with the water, and so the outer portion would be only in contact with the water. If we crush it up and make the surface area bigger, like salt, that's why salt is crushed up. So when you put it on, it dissolves in your food. And same idea. So questions on that. That's what happens. So we don't want to show the beaker and how it breaks apart, so we kind of show it this way. This is called dissolution, or dissolving, called dissolution. And when that happens, we show KBr solid. We draw an arrow, and then on this side we'll show the charges of those and how many we have. So that's a process called dissolution. You're just showing, and then probably put AQ here because they are aqueous now. So let me have you do one and see if you can do the same with the, well, I'll give you two. You need to draw them out to what you think they break down into, and we'll see if you're doing it correctly or not.
Are all of those aqueous?
These will all be aqueous because they're all going into water. Okay, so everything dissolution, it means it's, and we pretty much say it's in water that it's breaking apart into. So we'll give you two other ones to do. Then go ahead and draw those out, what you think, how they're going to look on the other side based upon the first example that we did. So sometimes students will take and split the S and have one S, and then they'll have O, and so they'll have three products of K, S, and then 4 oxygens. They'll do it that way. So what we do is we just have to recognize that the polyatomic ions stay together. And so this SO4 has to stay together. It's not going to break apart. Okay? So every time we have a, I guess an ionic solid, that's what these are, when they break apart, the polyatomic will separate from the other ion. break apart. Yes?
Is the 2 in front of the potassium just because there were 2 in the original?
Right, so it's kind of like moles.
Yeah, you're balancing.
Right, I don't want to put a 2 below because that's saying it's like it's diatomic and we'll have 2 potassium ions hooked together. We don't have 2 potassium ions hooked together. It's not like H2 and O2
You have 2
and
connected
N2.
to the...
But what we do is when it breaks apart, it comes in here as K2SO4. For every one that goes in, we get 2 positives and 1 SO4 minus.
Yeah, gotcha.
Is the positive always the first one?
And I always say in chemistry, I always get myself in trouble when I say always.
Most of the
Because
time.
when I say always, there's always exceptions to certain things. And we'll see some of those exceptions at times. But I would say 90-something% of the time, yes.
How do you know which ones are positive and negative?
Just where they use some material.
Well, sometimes if they're written out ionic, the first one's always a cation, the second one is always a negative ion. Yeah.
So like, that one's positive.
Yeah, so if they're metals out in front, they're going to be your positives. Or hydrogen out in front.
Positive,
Check
non-metals
your
are
oxidation state for your thing, like.
Yeah, and you can look them up on your charts or on the periodic table. They would just be the charges that you put together when you write formulas out. Okay, this next one.
I don't understand why we're writing all of that. Like, what's the point?
Because when
Oh.
they're in a solution.
Like, why do we split it up? Like,
Yeah.
what's the point of?
To show what it looks like in the solution. So when we split it up, that they start floating around in ions. And so this one, when we split it up, when we look, if we actually could blow everything up and see the actual particles in there, we would see 2 potassiums form for every SO4. It's kind of like Oreo cookie.
Oh, yum.
Yum, you bet. Double stuff. Yum, yum, right? You take it apart, you got 2 halves.
Yep.
You got your filling, that would be all together,
That's your SO4?
that would be like your SO4, and then you have your 2 cookie parts, and that would be like your K.
Why do you have a negative 2? That's what-
Because when you look at SO4 on your polyatomic ion chart, it's a
Oh,
minus
okay,
2.
yeah.
So you can always look on that, or you can tell it from K is a positive,
Yeah.
1, you got 2 of them, so SO4 has to be a negative 2. Okay? Good questions. It's good to see pictures. Good to see how things break apart. By the way, what would be the molarity of K compared to SO4? So this is just a general question. Mike, what would be the concentration of K versus SO4?
K would be double SO4.
It'd be twice the concentration. Because we're getting 2 atoms out for every 1. So the concentration of SO4 would be the same as the molarity that we found in the previous problem. I mean, if it's KBr, okay? And then K would be twice that original concentration because it'd be double. You'd be producing 2 for that. So this next one would be 2Fe positive 3 and 3 SO4 minus. Any questions on that?
Yeah. How do you get? Wait. Oh yes, I got that right. Look at that.
You just basically take the subscripts and put them out front.
We don't
Yep.
really care.
Do we need to know why, like, the numbers switch, like they go from the bottom to the top?
It's because the iron's not connected to itself. They're just 2 moles apart. Because it doesn't exist that way when it does.
When it breaks apart, it's not that. So like, while it says, well, Fe right there is like together, it's because it's formed one huge versus.
It's kind of like if I have a tricycle and I take it apart. When I take it apart, I'm going to end up with 3 wheels and 1 frame. Every time I take it apart, it's always going to be 3-to-1 ratio. Okay? That'd be kind of something that you can think about. Okay. We got 2 other problems that we're going to look at. Guys, ask questions. I know that some of you need that further explanation more than I can give you sometimes. And that's what I want to do once you get first time figured out. Okay, I'm going to put one problem up here, and we're going to go ahead and figure it out.
Oh, wow.
So how would I start this problem out? What would be a good starting point?
Figure out
For grams.
moles.
Okay, figure out grams of mole, and I've got the weight figured out, so we already have the weight figured out. And I would put that down, but you guys know to put that down. Some of you are detailed on that, some of you don't. It kind of gets you in trouble sometimes when you're not detailed. I noticed that on the test. Sometimes students don't want to go that extra mile to put down what they have at each step.
Is that 3 and 3?
And is that FE 3 or 5?
3.
3 and 3, 84 grams.
So that gives me moles of Fe3. So this is just like the other example. I have moles of Fe3SO4 Now this is like last, it'd be like chapter 2. And now what I want to do is I want to find moles of what? The question asked me to find the concentrated sulfate ions. So I want to find moles of what? Sulfate. So down here I'm going to put what? 1 mole of this, right? You think I would have picked a better one other than this complicated one to write out each time. That's the way it goes. And then what would go up above?
3 moles of sulfate.
How did you get 3?
Or 2 moles of
2 moles.
sulfate.
Yeah. Let me. We're gonna use this. Even the formula is wrong. It should be Fe2SO43. That's okay. All right. To show you this, we're just gonna leave it this way. Okay, because I'm not gonna go back and change all those. So how many SO4s? 2.
2.
Now what all do I need to do?
Now you need to go from 200 milliliters to...
Right, and let's just do that, and we know we can just divide it by 1,000 and put liters down here. So how many liters is that? So we have moles of SO4 over liters of solution. And so then we'd have molarity. Okay. 1 point, what'd you get?
3.2.
I don't know, I had messed mine up, so I'm trusting in you.
Yeah.
1.32?
Yeah.
Okay.
Good job.
And that's a SO4 only?
Yep. Just those ions, yes.
When you have a number that's like beyond like 3 decimal places, where do you want us to round off at?
What do you mean,
Besides-
beyond 3? I don't know.
Like certain elements on our periodic tables.
Oh.
It'll have like 50.
You can go to the hundredths place and be okay. I mean, I'm not gonna make any fast rules about that. Okay, last one, very last one. I know you guys are getting tired of this. Last one, just want to see one more example. Maybe kind of going the other way, where you have to figure out how much you need to dissolve in which to make a certain concentration. So let's say we have a certain concentration, and we have to make up this solution in the lab. And so we've got the solid, but we've got a solution we got to make up. And so I've got to go through a procedure to see how many grams I have to weigh out to make that solution. Yes, Alan?
On that problem, what if it was asking the concentration of iron? Like, how would you choose that? Like, how...
Just be 1 to 3. Up here it'd be instead of 2 moles, because like how it breaks apart,
Gotcha.
3 to 2. Okay. All right. Last question. So this one is the opposite of what we just did. So you would start out with 0.45 moles over liters. That's molarity. So a lot of times when we got molarity and we're using molarity and we're canceling out units, we don't want to just say molarity, because now if we put molarity, moles over liters, then we need to get back, we need to eventually get to grams of MgCl2. So we've got to change moles into grams, and then we got to get rid of L in liters. We got to cancel liters all the way out.
Wait, so is the 0.45 is that molarity or moles?
Yep, this is the same as this.
Moles and molarity. is
Yeah.
the same.
Moles over liters is the same as, in case someone's showing a capital M. So all problems where we're canceling out units and going through the process, we want to use moles over liters. Because if we use molarity, it makes it to where you can't cancel out your units to get to your final answer.
So that M is moles of
Moles
Cl
over- yep.
ions?
No, that big...
This M is molarity, which is moles over liters. And so what I'm doing is I'm telling you it's moles over 1 liter. Right? So my first step is what? You can go whatever you want to do. So what do we want to do first? Moles to grams. Alright, so I need to put moles of chlorine ions. So down here I want to put moles of chlorine, and up above, what should I put?
Moles of MgCl2.
Yeah, because I want to know how much MgCl2 I've got to dissolve. So I want to go from moles of chlorine to moles of MgCl2, right? So moles of MgCl2. So what would go down here? 2
3 1
to 1.
Oh.
So down below, you guys don't have to write this down, but this is what's taking place. We've got MgCl2, we form 1 Mg plus 2 chlorines.
Oh, sorry.
How can you have 2 moles of one thing if you only have 1 mole of the whole thing?
Because it splits apart into 2 parts for every one when it breaks apart.
Because moles is relative to what you're measuring.
So what we have is 2 moles of chlorine here, and we're going back to here. So it's a 2 to 1 ratio.
Oh, okay.
2 to 1 in your stoichiometry.
Okay, I see. Yeah.
Okay? And it's also here, you can get it from here, the formula says 2 chlorines for every 1 of the product. So now we got moles, and we're okay with that. We've got to find grams of that, though, so...
For every 1 mole of MgCl2.
Let's do our liters next, and let's get rid of those. So how are we going to get rid of the 1 liter?
1 liter over
milliliters.
1,000 milliliters.
No, just
Oh.
0.3
What do we want?
liters.
We want to get rid of L.
Put 0.3 liters over 1.
Can we put 0.3 up here and be okay with getting rid of liters?
Yeah.
Because we've got to figure out how many moles we have in 300 milliliters. And that allows us to figure out how many moles we could have in 300 milliliters.
And then you would just have to multiply by the molar mass.
Yeah, and then at the end we just have, now we got moles and it's just a straight moles to gram problem at that point in time. And then so that is, the relationship is 1 to 95.2.
Is that a 300 or 0.3?
That's 0.3.
So very powerful, the process of getting rid of units, either multiplying or dividing, get rid of them to come up with the final answer. That would get our final answer, and it should be like 6.43 grams. So if I wanted to make up 3 milliliters, I was doing a lab, and I do this all the time. There's students at college that will actually have a job on campus they can do. I'm going to try to talk my daughter into doing it. They actually go in and professors aren't going to make up all the solutions. They're not going to do all of that. But what they'll do is they'll have a lab assistant go through and he'll say, well, I need to have, to do this lab, I need to have 5 liters of a solution that has 0.45 molarity of chlorine ions in there. I've got to have that many, that concentration to do the lab. So they would have to go through and figure out how much they would need of the MgCl2, measure it out, mix it up. And that would be the concentration they would need to use. So,
You just mix it into water.
is that?
You just mix it.
Well, what you do to mix this up right is you don't quite have 300, you maybe start out with half that amount, so like 150. And then you put 6.43 grams in there, mix it all up, so it's all dissolved, and then fill it up to the 300 milliliter mark. Because if I put 300 milliliters of water, put in 6.43 grams and mix it up, my volume might be a little bit bigger than 300.
So you're mixing, so you're mixing the same solution with just the same solution? Like, I don't get that.
No, it's
What
a
are you
solid
mixing?
form first. It's water and so
So you're putting just normal magnesium into MgCl2?
putting in magnesium chloride into it.
Into what?
Water.
Water.
That's what I asked in the first place. With
Yep.
water.
Okay, I'm going to give you an assignment. It's not due until Wednesday.